Hello everyone. Today, we're going to work on this example, a simple pendulum system. The pendulum's angle is controlled by a force applied in the perpendicular direction to the pendulum. I'll begin with the multi-body template. I'll use this block to represent the rod. And I'm going to add a revolute joint to model the pendulum. I'll measure both position and velocity and define the damping constant. As for the outputs, Q stands for position, so its unit is radians, and W stands for velocity. It's almost done. As I said, this block represents the rod, so I'll adjust its dimensions like this. It looks good. Now, I'll define the inertia to be calculated from the geometry, then select mass. Okay, let's define the attachment points. I'll create a new frame and select the top surface to join with the revolute joint. Now, let's add the bob mass. The position from its edge to the center of gravity is 0.05 meters. So I'll use 0.1 meters. I'll also specify the inertia as a point mass. We need to define a frame to attach it to the rod. Okay, it has already been defined. Now, let's take a look at the rod. We should define another frame for attaching the mass. It should be the bottom one, here. For the actuation force in this direction, I'll add a frame to the mass side, normal to the local x direction. Then, I'll add the external force and torque block to the system. I'll select force and add the input, which is a 0.5 Newton step function. All right, let's see the results. Why doesn't it move? I think something went wrong. The diagnostic viewer says there's a mismatch in input and output dimensions. However, I think that's not the only problem. Let me see. The coordinates are correct. The rod is right here, but I can't see it. Well, I found it. It's lying down here. So, I think I forgot to rotate the global coordinate system. Exactly, I forgot it. Now, for the dimensional mismatch, we need 3 input dimensions. I think this one might work. The force is applied in the x direction, so I'll put it right here. And set the rest as 0. Okay, let's run the simulation again. Great. It behaves as it should. Let's move on to compare the results with the mathematical model. I'll begin with the transfer function. But before that, let me tidy up the model. Okay, to define the transfer function, we have to input these values. However, the given problem does not provide the moment of inertia. The moments of inertia for these two components are given by these equations. As you can see, there are many variables. So I'll load the parameters that I have created in the Pathline folder like this. You'll see that the parameters are loaded into the workspace. If you want to create a new file, define the parameters and use the save command. Type the desired file name here and the variables here. The file will be saved in the folder. Let's test the variable file. Okay, back to our model. I'll insert it like this because I have already defined it. Let's see. You'll see the results match like this. Now, I'll add the state space block to the model. In this block, you should input the matrices of the state equation. This is the A matrix and B. The output is the angle, so C is 1, 0, and D is 0. The results look perfectly matched, but they are not. When we zoom in, we'll see a difference. This happens because the actual system is nonlinear, while the mathematical models I showed here are linearized. From the equation, we can see that if we increase the angle, the difference will become more noticeable. Let's use a larger input force. From the time response, you will see the difference. And from the Simulation Explorer, you'll see the large angle, which is the main reason the linear equation cannot fully capture the system's behavior. Let's go back to a smaller input force. You'll see the improvement in accuracy. I hope you found this helpful. If you have any questions or want to see a specific topic, let me know in the comments. Thanks for watching, and I'll see you in the next video.